Okay, so in this part of the lesson now we're going to graph y equals sine theta and y equals cosine theta using the tables that we just completed. Okay, so let's start by graphing y equals sine theta. And by looking at the table that you should have there in front of you with your note, we can see that when theta, first of all, on our graph here then, just to explain something to you, we have the angles marked along the x-axis. Okay, so let's label the x-axis with a theta. All right, and the value of the trig ratio corresponding to that angle will be graphed along the y-axis. So looking at your table, we can see that sine 0 equals 0. So when the angle is 0, sine is 0. So we're going to put a dot there at 0, 0. Okay, when theta is 30, sine theta is 0.5. So at 30 degrees, we're going to put a dot at 0.5. When theta is 60, sine 60 equals 0.87, so almost at 0.9. It's a bit difficult with this app I'm using. Okay, that shouldn't be quite at 0.9, but you get the idea. 90 is 1, so sine 90 is 1. Sine 120, 0.87 again. Sine 150 is 0.5. Sine 180, of course, is 0. Okay, we'll keep going. Sine 210 is negative 0.5. Sine 240, negative 0.87. Sine 270, negative 1. Sine 300, negative 0.87. Sine 330, negative 0.5. And sine 360 is 0. Now we're going to connect those points as well as I can here with a smooth curve. Okay, let's remember here that this is a circular function. In fact, what we've done essentially is unwrap the unit circle. Okay, so it's important to remember that the sine curve and the cosine curve are not jagged. Okay, they're rounded, what we call sinusoidal functions. Okay, now let's graph y equals cosine theta on the same set of axes here so we can compare them. But first let's label this one as y equals sine theta. Okay, and now let's plot the points for y equals cosine theta. So the cosine of 0 is 1. So this graph starts on the y-axis at 1. Now cos 30 is 0.87. And cos 60 is 1/2. Cos 90 is 0. Cos 120 is negative 1/2. Cos 150, negative 0.87. Cos 180 is negative 1. Cos 210, negative 0.87. Cos 240, negative 1/2. Cos 270 is 0. Cos 300 is 1/2. Cos 330 is 0.87. And cos 360 is 1. Okay, once again, we're going to join these points with a smooth curve, if possible. And we'll label this graph as y equals cosine theta. Now there's a couple of things I want you to label right directly onto this graph, okay? There is some terminology that you need to be familiar with in terms of these trig functions. And one of those terms is the amplitude. Okay, the amplitude of a sinusoidal function refers to the difference between its horizontal axis, which by the way is the x-axis for both of these trig functions. Okay, but it will not necessarily always be the x-axis because we could translate these graphs up or down, which would move the axis along with it. Okay, but this, in this case, it is the x-axis. Okay, so that would be the axis of the curve. The distance from the maximum point down to the axis, or from the minimum point up to the axis, is called the amplitude. Okay, and if you've ever seen the graphs that occur on an equalizer or an amp for music, you'll see this type of graph, although it's a little more jagged than this one, occur. And of course, the louder the music goes, the greater the amplitude. Okay, and that's why we call that an amp, really. Okay, so one term you need to be familiar with is amplitude. Another one is the period of the graph. The period of the graph is the length of one cycle on the graph. So you'll notice that both of these graphs have like a smooth wave-like appearance. And the distance of one complete cycle of each of these graphs, which is what we have shown here, is called the period of the graph. Okay, the length of one cycle. Okay, so now we're just going to summarize some observations about both of these graphs in your note. All right, first off, we're going to say that both of these functions are what we call periodic. I'm having some trouble with the pen here today. Let's try this again. Guess I have trouble with the pen every day. Okay, the functions are periodic. Okay, and a periodic function, just to jog your memory, has some sort of repeating pattern. In the case of sine and cosine, that is sort of a wave-like, very smooth repeating pattern. Oh dear. Wave-like repeating pattern. Okay. Second thing I want you to notice is that the shape of these graphs is actually exactly the same. So y equals sine theta and y equals cosine theta are exactly the same graph, just translated or shifted 90 degrees to the left or right, depending on which one you're starting from. Okay, and the other thing is that neither graph ever goes below -1 or above 1. So the graphs never go above 1 or below -1. Now, when we get into transformations of trig functions, we will run into some graphs that do, in fact, okay, go outside those boundaries. Now, we're just going to fill in this table here to compare some other properties. So, in terms of the amplitude, which is something we just talked about, the amplitude of both of these graphs is 1. The period of both of these graphs is 360 degrees. The domain for each graph is the set of all real numbers. The range for both of them is a set of all y values between -1 and 1. So I remind you of this notation here to indicate that I'm speaking of all y values between -1 and 1. That's interval notation I'm using there. Okay. Same for y equals cos theta. The y values are between -1 and 1. We want to compare the y-intercepts for these two graphs. For y equals sine theta, the y-intercept is 0, whereas for y equals cosine theta, the y-intercept is 1, because of course the cosine of 0 degrees is 1. All right, the x-intercepts. For y equals sine theta are 0, 180, 360, and so on. For the y equals cosine theta, the x-intercepts are at 90, 270, and they would repeat every 180 degrees as well in both directions. Okay, next thing we're going to compare is the max and min values, which of course are the same for the two graphs, 1 and -1 for them both. And lastly, the equation of the axis is something we are often asked for trig graphs. And again, that refers to the horizontal axis that goes right through the middle of this repeating graph. And in both of these cases, the axis is the x-axis, which has the equation y equals 0. But again, if we shifted our graph up or down, that would change. Okay, so these graphs are both examples of what we call sinusoidal functions. Okay, they're periodic, but it goes beyond that because of the specific wave-like repeating pattern that we see in these graphs, and they're called sinusoidal functions. And that concludes this lesson.